Hello, I'm Timothy Rivette, and I'm going to be discussing fatigue. The title of the research paper I was assigned is The Cyclic Properties of Engineering Materials. The authors include N.A. Fleck, K.J. Kang, and M.F. Ashby. The journal this comes from is Acta Metallurgica et Materialia. It is volume 42 and it came out in 1994 and includes pages 365 to 381. This was received on July 12, 1993. The specific scope of study of this research is to analyze cyclic fatigue properties of engineering materials, which includes endurance limit, fatigue threshold, and Paris law constants, and compare them with static properties like yield strength or Young's modulus. The key question addressed is how can these properties be compared, organized, and beneficial in material selection? So the model used in this research include material property charts, which include endurance limit versus strength, or fatigue threshold versus fracture toughness, and also empirical fatigue models, which to the right we have Baskin's law, which is used for high cycle fatigue, Coffin-Manson law, which is used for low cycle fatigue, and Paris law, which is used for fatigue crack growth. There are many indices used in this research, and there are four main groups, which include infinite life for uncracked materials, infinite life for pre-cracked materials, elastic components, and damage-tolerant components. To the right, I just have the uncracked and pre-cracked infinite life indices, but all of these indices use endurance limit or fatigue threshold in the equation, and they're used with another parameter like density or Young's modulus. There are 6 different materials surveyed in this research. This includes metals, ceramics, polymers, elastomers, and woods and composites. So the first key result from this study is it includes the question, how does the relationship between endurance limit and strength affect fatigue performance? We have the plot in the middle of the slide, and the important material selection takeaway from this data is to select materials with high fatigue ratios for better fatigue resistance. This can depend on the situation, so steels are better for high load bearing parts, or ceramics are better for low weight but high stress applications. The second key result from this study is how does fatigue threshold relate to fracture toughness of materials? So for a low ratio, it's best for finite life where crack growth must be controlled. This enables life estimates using Paris law. For high ratios, the material can basically be selected solely on fracture toughness. The fatigue threshold is not much lower than the catastrophic limit. So this is the Ashby diagram I came up with for this research. It includes the fatigue threshold versus density. And this is helpful for lightweight designs that need a higher fatigue cracking threshold. And as you can see based on this plot, composites would be the most suitable for most applications. So some key conclusions from this research are fatigue properties correlate with static properties. Endurance limit and fatigue threshold often have correlations with yield strength, fracture toughness, or Young's modulus. Indices can guide optimal material selection. Many indices in this research were based upon real-world situations, and material classes have different uses for fatigue design. Metals were great for finite or infinite life. Ceramics have high fatigue ratios, and composites are great for lightweight designs. Some personal critiques of the usefulness and quality of this research I have are it was very comprehensive and design oriented. It involved data mixed with theory, and it was directly applicable to engineering design. One thing it didn't consider that much was the environment these materials were going to be in. So It didn't consider erosion or corrosion or any thermal fatigue. So that would be one thing I would want to mention with these materials. But overall, it was a great research.